Welcome back, everybody. I worked heaven and earth to get the exams and the essays back to you, and the reason for that is because this Friday, October 23rd, is the last day that you can withdraw from the class with no questions asked. All right? I wanted you to know where you're at in the class. After this Friday, you must see the dean, and you must have a good excuse to withdraw from the class. Up until Friday, you don't even have to see me. You just have to get the form and fill it out. Some of you might want to consider that. I never encourage anybody to withdraw from a class. However, if you look on your Scantron, the percentage, your current percent in the class up here, that is your current grade in this class. That is not the percent that you got on this test. That is the percentage of points you have accrued at this point, up to and including the extra credit and including the essay and so forth on the exam. So if you want to say, where am I in this course, that is where you are at. That ranges from like a 33% to over 100%, just to show you the range we have in here. I do want to mention I am extremely happy with how the test went. You made my week already. And it's been a lousy Monday. I've just been plain stupid this morning. But when I ran the exams and got everything together, I was very happy with what had happened on this exam. Now, what I'm going to put up here is just the raw stuff. Your score on the exam out of 40 is the red circled number plus 3. Okay? So your score on the exam is the circled number plus 3, because I'm still curving at 3 even though you did much better, plus the score on your essay out of 40. And of course that's a percent. So if you had a 25, then you add 3, that's a 28. If you got a 2 on the essay, that's a 30 out of 40 or a 75%. Okay? The current grade includes all possible points that you have accrued at this point. I am happy to say that without the plus 3 curve, the average was a 22.6 or a 57%. Now that might seem bad. That's typically what I see during the first test in the normal semester. The key thing here is that that is 13 percentage points higher than the 44% that we saw on the first exam. So there was a huge increase in performance. I anticipate it will still go higher. People are figuring out how to do this online thing even though we don't love it. We're stuck with it for the moment, and so we'll just have to make the best do, okay? So the high score, without adding on the plus 3, the low was an 8, and that is a 20%. And the high, actually no, these include the curve. So you can see it went from 20% up to 100%. We got the full range of people out there that were doing things. But the key thing was it was over almost a letter grade and a half improvement over the first exam. So congratulations at least on that. And I think if we study a little bit harder and you get into the groove, it will do even better, okay? But still, there are still plenty of people that were very, very low. And And it's up to you to decide whether or not you want to continue in the class, but you must make your decision by Friday, otherwise you're going to be facing seeing the dean. Okay? I don't think this course is typically offered over the winter break. It is offered in the spring again, and of course you should know that given circumstances, you can do grade forgiveness and so on and so forth. So if things aren't looking up, there are opportunities still available to you. Okay? Any questions out there? Yeah.
What is grade forgiveness?
Pardon me?
What is grade forgiveness?
Grade forgiveness essentially says that given certain requirements, you can retake a course, and the second grade takes instead of the first one. Now, if the second grade is lower, that takes two. That's the way it works. That's the way it works. Many students will use that option when they get near their senior year. They realize that their GPA is too low, and they realize that if they retake a course, they can raise their GPA, especially if they got a very low score in that the first time through. It doesn't have to be through the same instructor either. And I am not going to be teaching in the spring. I'm going to be on sabbatical. So I will be gone from here for almost 9 months. Then I'll be teaching this again in the fall. But grade forgiveness, you have to check with your advisor. There's only a certain number of times you can use it. There are restrictions on how many hours you've accrued. I don't know what it is. It's all on the handbook. But it's a very important option. It's a very, very important option. Any other questions? Good question, that's a really good point. All right, well, we're getting into one of my favorite chapters. I like the whole course. I love the whole course, but we're getting into one of my favorite chapters because I did work specifically in this area. I was at Los Alamos National Lab doing antimatter physics for several summers. What an experience that was. I wouldn't want to live there. It can get a little bit lonely. I mean, it's a small town, and it's a small town like Frostburg, and you got miles and miles and miles and miles of desert before you get to Santa Fe. It's not like you got Cumberland here and then, Hagerstown, and then no. And it's at 6,000 feet. So you will get a headache and nosebleeds adapting to that altitude. And they have a beautiful ski area there up at 12,000 feet. You will get dizzy unless you acclimate to that ski slope. So, the idea that we're going to get into now is relativity. Now, relativity is not new. Relativity goes back hundreds of years. But special relativity is only about 100 years ago. And also, according to what I looked at, I have to look at the schedule on Canvas myself to keep A and B straight and so forth. Our next exam will be 3 weeks from, in about 3 weeks, so that's how much time we got. The last exam, let's mention that too, you'll see that we're covering less material for these successive exams, so the exams count the same amount. So that means it's very important that you keep up on it. So I think the last exams will be fewer questions perhaps, but you have less time to study for them. So, it kind of evens out. Special relativity versus Newtonian relativity. Newtonian relativity obviously is the relativity that was in force back in the 16 and 1700s and up until about 1905. So we're going to start by talking about Newtonian relativity and understanding what relativity is. And then we're going to start getting into electricity and electromagnetism. Electricity and electromagnetism play a huge role in this subject. And as I mentioned, we will see that time travel, at least forward in time, is possible. And by time travel, I don't mean you can just step through a window like they do in sci-fi and suddenly be in the past or whatever. You have to enter a machine, spend some time there. I mean, when you travel, you spend time traveling. It's not instantaneous travel. That you can travel to the future. So in the movie sequence Back to the Future, there's nothing wrong when Marty goes back to the future. The trouble with the whole movie is in the beginning of the movie when it goes into the past. That you cannot do. That you cannot do. Okay? It all starts with a subject which might seem uninteresting, but as always happens when we start to look closely and make careful measurements, we start to discover that there are problems. The initial subject that we have to talk about is frames of reference. This has to do with how we measure position and velocity and acceleration and so on and so forth. Now, the easiest thing to visualize is measuring position. What you have to do, if someone says, where is so-and-so in this particular room? Well, the first thing I have to do is I have to choose a starting point. What we essentially do is we choose three directions that must be mutually perpendicular. These are mutually perpendicular. They're all at right angles to each other. So are these. But if I do this or this, these are not mutually perpendicular. The angle between each ruler and any other ruler must be 90 degrees. However, the orientation is arbitrary. And when something is arbitrary, that means it's up to you. You choose what is convenient. In a room such as this, it kind of makes sense to choose to the left, to the right, towards the board and towards the back of the room, and up and down. Though there's absolutely no reason we couldn't do this, or this, or this, but considering the orientation of the walls and the desks in the room, it makes sense and it's convenient to choose this. So first we choose three mutually perpendicular directions. Mutually perpendicular directions. We often draw this on the board as something like this, where this is into the board and this is out of the board. It's hard to draw it in a two-dimensional space. And we'll typically call this X, Y, and Z. Okay? These are called our coordinate axes. And these are arbitrary. You choose what is convenient. You choose three coordinate axes. Now the coordinate axes intersect. And where they intersect is up to you again. Typically, a human being chooses a coordinate system. If I asked you to choose your own coordinate system, if you're outside or whatever, and not in a room, typically what you'll do is you'll choose up, down, in front of me, behind me, to my left, to my right, and you usually put the crossing point about here. You reference everything kind of to here, in front, behind, left, right, up, and down. Where the axes cross, that is called the origin. You choose a point where the axes cross. This is called the origin. And once you have chosen a particular origin, then you choose the three mutually perpendicular directions. then you have chosen a frame of reference. And this too is arbitrary. You can choose it any way you want. And then, when you specify the position of an object, you essentially count how far, if we're going to measure position in this system, the position of an object is given by 3 numbers. How far do you go, say in this room, if I use the coordinate system front, back, left, right, up, down. If I wish to locate something, I say from the origin, how far left or right do I go? Okay, how far left, right, how far up or down? Let's do it consistent, let's do down, up. And how far backwards and forwards. Typically, we can make things easier by putting in a mathematical sign convention, saying that left is negative, right's positive, down is negative, up is positive, back is negative, front is positive. We can typically do that. So if I wanted to specify the position of something, I might specify something like this, where m is in meters. It could be in feet. It could be in feet. So if I specify the position of someone or something in this room, I could say from wherever the origin would be, I could say, for instance, I'm going to put the origin right where the camera is, but on the table. So I could put the camera position right below the camera on the table. That's 0. Then I could say you go 3 meters forward from there. Then you go 2 meters down, and then you go 6 meters. Let's see, the left and right. We say this is left, right, down, up, back, forward. So I would say you go 3 meters to the right, then you go 2 meters down, and then you go 6 meters to the front, this direction. And wherever you wind up, that's the position. If I wanted to specify somebody back there in the classroom, looks like, Aiden, I'm going to use you. If I go over, I would say 2 meters. So, how do you spell A-I-D-E-N? Yeah, A-I-D-E-N. His position, let's see, left and right, from here over to, you're about 1 meter to the left, okay? So you are at -1 meter. It means starting at the camera, you go to the left 1 meter, then you got to go back maybe 4 meters. So back means -4 meters, and you're neither up or down compared to the table. I'll use this as your position. So to get from the camera over to Aiden, I have to go left 1 meter, then I got to go up or down none, and go back 4 meters from the camera position, and there's where he's at. I could assign the position of everybody in this class using this method. Every person has a different, unique position in this class. Position is to specify the position of an object. You must specify the coordinates. These are called the coordinates. But if I say somebody is 3 meters forward, 2 meters to the left, and 6 meters up, does that tell you where they're at? If that's all I give you? No. No. it's just like in Raiders of the Lost Ark when they're searching for the Holy Grail. I guess that's the third one. They know all of the directions except what? The starting point. They don't know the origin. So the specification of a position, first of all, requires a frame of reference. You have to know what it is. And then the instructions on how to go from the origin to that final location. I think you will agree, do these numbers change if I should change where the origin is at? If I put the origin where I'm at, well, that's going to change some of the numbers. If I put the origin up here or over here, the numbers depend on the origin. What if I, instead of using these directions, what if I use these directions? All the numbers will change. If the numbers that describe something change when you change the frame of reference, we say that that quantity is a relative quantity. Relative quantities depend on the frame of reference. That's what it means to be relative, because it's relative to a certain set of directions and a certain origin. So, relative quantities depend on the frame of reference. That's what you mean by a relative quantity. If it is not relative, then it is what we call invariant. Invariant means it's not relative. Okay, invariant quantities, we often think of these as absolute. Another word for this is absolute quantities. Do not depend on the frame of reference. Does the number of people in this room depend on the frame of reference? No, no. Does the number of rulers that I'm holding depend on the frame of reference? No. Does the distance on the board from this point to this point, does this distance depend on the frame of reference? No, it does not. Does the position of each dot depend on the frame of reference? Yes, but distances do not. Okay? Distance does not. Does your weight depend on the frame of reference that I use in this room? No. So some things are relative. You don't say everything's relative. That's rubbish. Some things are relative and some things are not relative. It just depends. Okay? Most importantly, the examples of invariant quantities, recall Newton's absolutes were time, distance, not position, distance is different, distance, and inertia or mass. Newton held that these three are invariant. However, there are many things that are relative. There are quite a few things that are relative. So if we look at things that are relative, position, obviously. Velocity. Okay. Energy. An example of this is we can ask how much potential energy does this timer have, gravitational energy now. Well, compared to the, if we use the tabletop as a reference, it's got some energy. Okay? But if I use where it's at as a reference, it has none. Another example is altitude. You say, how high is this desk? You say, I don't know, about 3 feet. Well, yeah, but it's 2,300 feet above sea level. So the choice of origin affects the altitude of this table. That's relative. Okay? Energy is force or no. So let's make a list here. Invariant. Time, distance, mass, force, acceleration, you will find that you can get an accelerometer. In fact, many phones now contain an accelerometer that can measure acceleration. So even though the velocity may be relative, the change in velocity over the change in time is not relative. And force, which is mass times acceleration, it's invariant. Okay? Position, velocity, energy. We'll find other things over here. Electric charge. Temperature is a big one. Temperature is invariant. Temperature. But when I say energy, I mean kinetic energy, gravitational energy, and so on. There are many relative things here, and there are many, many invariant things. And this is what we call Newtonian relativity. Whoops. I think I need to get a new marker, but I'll try and work this one out. Also, this was about Galileo. This was known in Galileo's time, so it's often called Galilean or Newtonian. Galilean Newtonian relativity. Now, there are some problems. And one of the things I really like to use, if you watch Turner Classic Movies, they have what are called film noir, which are films about crimes and gangsters and all this kind of stuff. And what will often happen in these old films, if you have somebody that you want to get rid of, but you don't want to kill him, you're not the really, really bad guy. You Shanghai them. Does anybody out there know what it means to be Shanghaied? Okay, does anybody know what is Shanghai?
No, it's a city.
It's a city in China, okay? Well, back before airplanes, the only way to get to China was on a boat. A lot of honeymoon couples would take a slow boat to China. Okay, there's a song called I Want to Take You on a Slow Boat to China, because you can fool around the whole way and fool around the whole way back and sit on the deck. It's not like these things they got now. Okay? Anyway, if you wanted to get rid of somebody for a while, you knocked them out. You had a thug go and knock them out, or you drugged them. This has to be in San Francisco. Okay, that's not Chicago, it's San Francisco. Then you take them down to the docks, and there's some sort of a boat leaving for China the next day. You buy them a ticket, shove it in their pocket, and you say, this guy got really drunk, but he's leaving. You know, you put him in a room and let go, and he wakes up out at sea. Okay? And of course you take all their money too. So now it's going to take how many weeks for this person to get to China? They're going to be broke when they get to China, so they have no way. It's a one-way ticket, by the way. All right? They have to find a job, make money. If they, you know, it gets rid of them for maybe a couple of months. Okay? This was done quite often. Well, imagine you have been shanghaied, and you suddenly wake up in a room, and you can't look out. You may not even know you're on a boat. You just wake up in a room, right? You can make a room on a boat in any shape, decorate it any way you want. And you ask the person, are you moving? See, are you moving? Well, normally I think they would say no. Of course, what would happen if the ship happened to heave a little bit? Whoa, okay, yeah, something's going on here. But if the boat doesn't heave, if the boat is extremely steady, there's no way to tell. In fact, what if I shanghaied you, but I stuck you on an airplane? And a private airplane with, that again could be made up to be just about any room. And I told the flyer to take you up and fly you at 500 miles an hour, but maintain absolutely steady flight on a clear day with no turbulence. And you wake up in the room, and I say, are you moving? Would you be able to tell? No. See, this has to do with measuring velocity. Velocity depends on the frame of reference. So does position, so does energy. If we were to go into space, okay, let's use a train. Let's also use a train. That's even more realistic. They got some high-speed trains in Europe that are really, really smooth. They go 300 miles an hour. So you put somebody on a train, you wake up on the train. Have you ever woken up and not know where you were at? Oh yeah. It's like, whoa. Especially when you're on vacation. You don't see, okay, you suddenly, but you're on a train, and you wake up, and the train is going smoothly. You can't tell. What if the train, though, slams on its brakes? Well, now you're, whoa, something, whoa. You can tell, you would say you're moving, but actually, you can tell that you're accelerating. How does the train have to go so that you can never tell? You tell me, how must the train behave such that if you do any experiment inside the little room on the train, you cannot tell that you are moving? Can the train speed up or slow down? No. What else must the train do? Can the train go around a curve? No. If a train goes around a curve, if I put this on the floor and it goes around a curve, this thing will roll to the outside. See? Well, that's what we call a non-inertial frame. When you talk about frames of reference, the question you can ask is, all right, this frame of reference set is arbitrary. I can choose any frame of reference I want, including one that is moving. When you get on a train, what frame of reference do you use? You put the origin at your seat. And the front of the train, the back of the train, left, right, top, bottom. If the train happens to go around a curve, your frame of reference turns with it. Frames of reference do not have to be sitting still. It is totally possible, for instance, if you go to an amusement park, it is totally possible for you to be in a frame of reference where the coordinate axes spin or change direction. And when that happens, you can tell. You can tell. Even if you were out in space where there's no gravity, If the coordinate axes were to turn, you could tell. You would be able to tell. You would be able to tell. If you were out in space in a room, and I'm talking about away from Earth, everything, of course, would there be any gravity? No. So here you are in this big room floating, and the room's around you. If the room rotates, you're not going to rotate. There's no force on you. You're going to see the room rotate. You say, whoa, someone's messing with the room here. Okay? What it comes down to is you can tell if you're accelerating. You can make measurements and you can tell if you're in an accelerated situation. But if there is no acceleration, you cannot tell if you are moving. Okay? You can tell if your frame of reference is accelerated. Acceleration is a big deal here. You can tell if your frame of reference is an accelerated frame of reference. And how do you know this? It's simple. If I were on the train, the easiest way to imagine this is just imagine a basketball. And the place where you can actually do this, which is really cool, people look at you weird, but who cares? You go down to Washington, D.C. and you get on the metro. I love the metro, man. I love to be able to go around and you put a basketball down on the floor. You put a basketball down on the floor. What will happen to the basketball? And I have my camera with me. My camera is fastened to the floor of the train, and it's pointing at the basketball. Now it's a pretty boring movie, okay? But better than some I've seen come out of Hollywood. Anyway, we won't go into that, okay? What will the ball do, if anything, if the train doesn't accelerate? It'll just sit there. But what if the train speeds up or slows down? It moves. Specifically, it accelerates. What if the train goes around a corner? It'll move. That's a violation of Newton's laws. Newton's laws say that objects accelerate only when there is a real force causing the acceleration. But in that situation, you will see the ball sitting there, and suddenly it starts to move, which means it accelerates, even though there's nothing blowing on it, pushing on it, pulling it, tugging it, or anything. That violates Newton's laws of motion. And that is how you tell if you are accelerating. You check Newton's laws. You say, do I see things accelerated when there is no apparent force causing the acceleration? Suppose I put the camera in a car, in the passenger seat, pointed at me, the driver, and the camera is fully fastened to the floor. And then I don't go too fast. I've got a helmet on too, okay? And I drive into a brick wall at about 10 miles an hour. What will you see happen to me? I'm not wearing a seatbelt, by the way. I'm a stuntman. Yeah. I am thrown to the front of the car. Thrown by what? There's no rope tied to me. There's no electrical force pulling me to the front of the car. There's no gravity pulling me. There's a fictitious force. I accelerate even though there is no force. Okay? This is called a non-inertial frame. There are two kinds of frames of reference. You can tell if your frame of reference is accelerated. The answer is, are Newton's laws violated? Or I could say, apparently, okay? Violated, Okay? Yes, then you are accelerated. So if things accelerate and you can't account for the acceleration, then Newton's laws are violated, then you're accelerated, and this is called a non-inertial frame of reference. I'm not going to write the words of reference anymore. This is a non-inertial frame. Newton's laws aren't valid. Things accelerate on their own. Things accelerate on their own. If you had that ball on the train and you had an incline in front of it, if the train decelerated hard enough, could you make the ball roll up the incline? Yeah, yeah. If they're really slamming on, yeah. You watch that in the camera and you go, whoa, there's nothing acting on that. That's a non-inertial frame. Okay? So a non-inertial frame or an accelerated frame. So there are two kinds of frames of reference. A non-inertial frame or an accelerated frame. And if Newton's laws, at least within your ability to measure them, show that Newton's laws are being satisfied, then you have an inertial frame. Newton's laws are valid. So there are two kinds of frames of reference. An inertial frame where Newton's laws hold, and a non-inertial frame or an accelerated frame. And in this case, I should include this here, this is an unaccelerated frame of reference. Unaccelerated. It comes down to, are you accelerated or you are not accelerated? Now, let's talk about this frame of reference. In this room, if I put a basketball on the floor, does it start moving on its own? Not really, no. For all intents and purposes, this room is an inertial frame. But you see, in actuality, now what's unaccelerated means, what's our velocity? Can your velocity change if you're unaccelerated? No. Now, here we're getting to it. Are we moving? Strictly speaking, are we moving right now? Well, the Earth is turning on its axis, and the Earth is going around the Sun. It's turning and going in a circle. Technically, this frame of reference is a non-inertial frame. But you have to do very careful experiments to prove it. And you know what one of those experiments is? It's the most famous experiment ever done. This experiment typically costs about $1 million to do, and it's right there in the hallway outside this room. It's called a Foucault pendulum. You see, according to Newton's laws, if you start a pendulum swinging, the direction of swing must not change. It can't start here and then a little bit later be swinging that way, and then later be swinging this way, and then later be swinging this way. Yet if you go out there and you watch that pendulum over a few hours, the direction it swings changes. Okay? Because the Earth is essentially, think about if this were swinging at the North Pole like this, and the Earth were turning below it, you and the Earth would be doing this, you'd be doing this, but it would be swinging like this to somebody off the surface of the Earth, but you see it rotating. So technically speaking, this room is a non-inertial frame, but it depends on how carefully you can measure it. The key thing is this. You can measure your acceleration, and you can determine whether it is 0 or not. You can measure your acceleration. In fact, we have accelerometers. Many phones now have an accelerometer in them. And believe it or not, if someone knows what they're doing, and if you have a really fancy phone with a very accurate accelerometer, they've done this in the lab now, not necessarily out there, but they can take your phone and by measuring its accelerations as you tap or write on it, they can figure out what you're writing onto the pad or what you're typing into the keypad in the way of a password. Okay, so somebody can, if your phone's open, they get in, they can read the accelerometer, they can figure out what you are typing. So be careful. Okay. Now here comes the $64 trillion question. Suppose you measure your acceleration and you say, to my ability, like you do here, you say, I'm not accelerating. I am definitely in an inertial frame. I've done the most sensitive experiments, even more sensitive than a Foucault pendulum. As far as I can tell, I'm not accelerating. Now I ask you, great, are you moving? You're not accelerated, but are you moving? As we are going to see, that cannot be answered, and that is going to have amazing consequences for everything we know about nature. Let's stop right there.